the file you upload, the message you read, all happens on Ethernet before you get it. So dive with me and get to know what is Ethernet and most of its concept as we go by. So this is chapter 5. This is chapter 5, CCNA 1, Introduction to Networks. So these are the objectives. I'm going to dive deeper in Ethernet protocol, LAN switches, and address resolution protocol. So on Ethernet protocol, I'm going to talk about Ethernet encapsulation, how encapsulation is done. And encapsulation, this is just the wrapping of the real data with the additional header, so that this header provide more information how the data will be received when it reaches the destination. Ethernet operates at the data link and physical layer, as you can see. So that at the data link it operates at 802.2, then physical it operates at 802.3. So Ethernet relies on two separate sublayers, that is logical link control and media access control. So on the encapsulation, that logical link control sublayer handles the communication between the upper layer and the lower layer. This is implemented in software and it is implemented independent of the hardware. MAC sublayers. The MAC sublayers has two responsibilities, that is data encapsulation. It ensures that the data is in the correct format or wrapped in the manner that it should be received by the recipient. Also, it determines media access control, or it handles media access control, whereby before the data is placed on the media has to be checked whether there will be collision or not. And also, when it comes to data encapsulation, it handles frame delimiting, addressing, and error detection, so that I'll explain them as we move by. But so how has Ethernet evolved? So that since 1973, the Ethernet standards have evolved, moving faster and more flexible versions of the technology to the update. So that you may find that initially Ethernet used to operate at 10 megabits per second, that is 10 Mbps, but right now the current Ethernet that we have, it has the capability to operate at 10 gigabytes per second, which is much faster. So we've got Ethernet frame. This is like the frame, the structure of an Ethernet frame. So the structure of an Ethernet frame, you should understand that the minimum Ethernet frame that can be sent, and the maximum. So the minimum should be at least 64 bytes and the maximum should be 18 bytes. So below 64 bytes, that is what we call runs, smaller bytes that cannot be transmitted, and the frame that is above the maximum, we call it giant. So those are the things that you happen to check on a switch when you are experiencing network downtimes or network intermittence. So that this is the frame. The first section, we've got preamble. This one marks the start of the frame. We've got destination MAC address. This one identifies the destination. We've got the source. The source marks with the machine that is sending, or the source that is encoding the message. That is, we've got ether type. Then the data is here. Then we've got FCS, frame check sequence. So this section, it deals with the errors. It checks the frame whether there is an error, and the error it might be that the frame to be transported or to be delivered maybe has not met the minimum requirement, or it has passed the maximum requirement. So that's an error that is meant to be handled by this structure, FSC, frame check sequence. So all those things that I have explained here, they are here. that frames less than 64 bytes are called collision fragment or rand frames or general rands. Automatically they are discarded. And frames less than above 1500 bytes of data are called jumbo or baby giant or giant frames. If the size of the transmitted frame is less than the minimum or greater than the maximum, the receiving device drops that. So you should understand that. That is a lab. Representation of MAC address. That a MAC address is an Ethernet address which is a 48-bit binary value expressed as 12 hexadecimal digits. That's 4 bits per hexadecimal digit. You find that hexadecimal is used to represent the Ethernet MAC address, whereby also in IP version 6 address that it runs from 0 to 9, so that is normal, but from 10 to 16 it picks from A to F. So it is easier to express a value as a single hexadecimal digit than as 4 binary bits. This is the critical section that you have to understand how it works, because it helps network engineers a lot. So MAC address, Ethernet identity. So like the MAC address is to summarize this, the MAC address is just structured in a way that the first bits, the first 3 bytes, that's 24 bits, represent the organization or the vendor. In summary, it is called the Organizationally Unique Identifier, OUI. So every vendor has the first 3 bytes very unique, marking that vendor or identifying the vendor in the industry. So that IEEE requires a vendor to follow 2 simple rules: that all MAC addresses assigned to network interface cards or other Ethernet device must use the vendor's assigned organizationally unique identifier as the first 3 bytes. All MAC addresses within the same OUI must be assigned a unique. So that's what you should check. You may find, just an example, HP has, when you check machines from HP, their Ethernet types have unique 3 bytes. The first 3 bytes are very unique, identifying the vendor. So frame processing. How is the frame processed? The MAC address is often referred to as a band-in address, that's BIA, meaning that the address is encoded into the ROM chip permanently. When the computer starts up, the first thing is that network interface card does is to copy the MAC address from ROM to chip, from ROM to the RAM, so that when a device is forwarding a message to an Ethernet network, it attaches the header information to the frame. You see, the header, that is the data, is attached to the frame, so that the header information contains the source and the destination, identifying where the frame is coming and where it is intended to go. Just as in this picture you can see, this is destination, this is the source. So MAC address representation. So this is, if you want to check how MAC address is represented, you can we can check here. We can check here IP. Let me zoom a bit. IP config. So you see, this is the MAC address. Just a bit. This is the MAC address for this machine, the physical address. So this kind of address is banned into a chip, and you find that these 3 bytes, this one, this one, this one, identifies the vendor. So that's what you should master here. And these are the commands that you can use to verify or to get to know what is the MAC address for that particular machine. The MAC address is the physical address for the machine. So we've got 2 scenarios here. We've got unicast MAC address and multicast MAC address and broadcast MAC address. What happens to these types of MAC address when they are in Ethernet structure. So that you find a unicast MAC address is a unique address used when a frame is sent from a single transmitting device to a single destination. That is one-to-one. In this scenario, this is a unicast MAC address. In this scenario, the frame will be delivered. But in a scenario whereby multicast, a frame is intended to go to a group of devices within the network, that frame will be forwarded to all ports except the incoming port. Same applies to broadcast MAC address, whereby it is intended to deliver a frame in all. So the switch is not so that intelligent as a router. It will just forward all, it will just flood the network except the incoming port. You can see many network protocols such as DHCP and ARP use broadcast. So that for a machine to get IP address, it first of all uses broadcast. It broadcasts a message to all nodes in the network to find where the server is. And you see in that sector, that's how it works. So these are two common protocols that work on broadcast. A broadcast packet contains a destination IP address that has all ones. It means signifying the entire network that the packet is intended, or the frame is intended to go to every node on that network except where it is coming from. When the IP version 4 broadcast packet is encapsulated in the Ethernet frame, the destination MAC address is the broadcast. So check how the broadcast MAC address is written. It's FFF for 40, composing of 48 ones in binary. So multicast, this one I had talked about, that allow a source device to send a packet to a group, to a selected few individuals or a few nodes on the network. As you can see, two are isolated. So when it is all of it, that is broadcast. But when 3 or more in that group, that is multicast. And there is a specific IP version 4 address that is for that. That is 224.0.0.0 up to 239.255.255.255.255. So that is it. When it comes to IP version 6, we use FF00:8. So this is a network you can use to verify the MAC address. So LAN switches, local area network switches. So these are the switches that are used within the private network, and these switches seems to be different from the ones that are used in the data center or in the distribution hierarchical layer. So I'm just going to explain more on this, how a switch functions. That a layer 2 Ethernet switch makes its forwarding based on the decision of Ethernet MAC address. That the forwarding of frames within by a layer 2 switch, that is 2960, it is based on Ethernet MAC address. It checks basing on the source and destination, so that a switch, when it's powered, the MAC address table or the CAM table is always empty, but it is populated as the switch tends to identify the connected nodes or the connected machines. As you can see here on this table, the table here, the MAC table is empty, but when the switch finishes powering, then it notices that some 4 machines are connected. So the port vis-a-vis the MAC address will be populated in the table, and that's what will help it to forward the frames. So how does the switch learn MAC addresses? That the switch dynamically builds MAC addresses table. The process to learn the source MAC address undergoes through this. That a switch examines all the incoming frames or the new source MAC address information to learn. If note these conditions, that if the source MAC address is unknown, it is added to the table along the port number. If it is unknown. If the source MAC address does exist, the switch updates the refresh timer for that entry. By default, get to understand that most Ethernet switches keep an entry for 5 minutes, beyond which they are deleted or removed. The process to forward destination MAC address includes that the destination MAC is a broadcast or a multicast. The frame is also flooded out of all ports except the incoming port. This statement, I had talked about it earlier before, that when the type of MAC address is multicast or a broadcast, the switch tends to forward all the frames related to that to all ports except the incoming port. If the destination MAC is a unicast, that is where the switch will look for a match, then it delivers the frame. If the destination MAC address is in the table, it will forward the frame out of the specified port. If it's not in the table or a non-unicast, that one is treated as a multicast or a broadcast, where it is forwarded to all ports except the incoming port. So filtering frames. As a switch receives a frame from different devices, it is able to populate the MAC address by examining the source MAC address of every frame. When the switch's MAC address table contains the destination MAC, it's also filter the frame and forward out of that single port. So that's what you should understand, how the switch filters the frame, that it checks the source MAC address is what guides it to determine the filtering. So this is a video that is just explaining how a frame is received and examines the source MAC address and notices that the MAC address is not in the MAC table. So what it happens, it will forward to entire switch ports except the entire connected device except the incoming port. So next, the switch examines the destination MAC and notices that this MAC is not in the table, so it floods to all ports. So the computer is going to send a packet to the internet because the destination IP address is on another network. In this scenario, for communication to happen with the remote network, we factor in the default gateway. So the default gateway is a special type of address that helps one network get connected to the other network. So this is how you view the MAC address table. You can connect two switches, then on each switch one computer, and then check how the MAC address is populated there. So frame forwarding methods on switch. In summary, we've got two methods. We've got store and forward, and we've got cut through. These are two techniques that a switch uses to forward frames. The first technique, store and forward. A store and forward switch, it receives the entire frame and computes the cyclic redundance check. This just means that it checks if the frame is valid and all possible errors. If the switch looks up the destination address, then determines the outgoing interface. In summary, store and forward, the switch takes the entire frame, checks the possible errors, checks all the possible source and destination MAC address, then it determines where to go. But cut through, the frame is entirely received. The frame is forwarded before entirely received. It means there is no that latency that is used maybe in checking whether the CRC is okay or the destination. The frame, once it is received, it is forwarded before it is checked, you see. So in terms of overhead, store and forward has high overhead compared to cut through. This one is responsible for real-time application that needs updates than whatever that is being sent. So In cut-through, the switch buffers just enough of the frame. It means that the memory buffers of the switch in this technique, they are so much large to accommodate the frame and all those appending parameters. The switch does not perform any error checking on the frame, that is on cut-through. There are two variants. So just know that cut-through, the error checking is not checked. The parameters like the source MAC address and destination is not also checked. But when it comes to store and forward, such parameters are checked, and that one makes it to delay a bit compared to its cut-through. So there are two variants or types of cut-through. We've got fast and forward that offers the lowest level of latency because the switch immediately forwards a packet after reading the destination address only. This is most typical form of cut-through switches. And we've got also a fragment-free switching, which is a hybrid between the cut-through and the store and forward. Memory buffer. So this is also a high area that is examinable in CCNA. They can give you a question then or a scenario to determine the type of memory buffering method used. So we've got two types here. But before we get to it, let's understand what is a memory buffer. That it is a technique to store frames before forwarding them. Buffering may also be used when destination port is busy due to congestion, and switch stores the frame until it can be transmitted. So we've got port-based memory, whereby frames are stored in queues that are linked to specific incoming and outgoing ports. And we've got shared memory, whereby all frames are deposited into a control buffer or a common buffer, which is shared by all ports. So duplex and speed. Remember, we've got full duplex. It means both the sender and the receiver can send and receive simultaneously at the same time, that is. But a half duplex, only one end of the connection can send and the other end can only receive. So when we've got mismatch in duplex, that is also you incur the network hitches or downtimes. If one side of a switch is operating at a half duplex and the other switch is operating at full duplex, the connection will not be so good. And that's where we kick in the concept of auto negotiation, whereby the two ends discuss and come to a common agreement at a speed or a duplex mode they gonna function. If it is a half, let both ends be at a half. If it is full, let both ends be full. Same applies to speed. Speed, one side of a link cannot function at, for example, 10 Mbps, and the other end is operating at 100 Mbps. There will be loss of frames. So auto negotiation helps to ensure that there is a balance, and in that scenario, the sender can send the information that can be processed by the receiver without any hitch. So duplex or speed mismatch is a common cause of performance issues within Ethernet links. It occurs when one port operates at a half duplex while the other port operates at a full duplex. So this is solved through auto negotiation, whereby the switch has that inbuilt capability whereby it can negotiate what is the best speed, what is the best duplex mode it can function. We've got auto MDIX. This is a technique in the new version of switches whereby it determines the correct link or the correct cable that is suitable between the nodes. For example, different devices are connected using copper straight through. When I say different devices, I mean it can be a switch to a router to a computer, that is a host to a switch. But when it is similar devices like a switch to switch or router to router, we use crossover. And you should know how to terminate or to crimp such kind of cables. We've got TIA 568B or TIA 568A. So if it is A and A, both ends, that is a straight through. If it is B and B, that is a straight through. If it is a mismatch, one end is A, TIA 568A, then TIA 568B, that's a crossover. So you can use this MDIX auto on the interface to ensure that the interface will negotiate the type of cable to be used. So next slide is address resolution protocol. In summary, this is a protocol that is used to identify the IP address that should be mapped to a specific physical address. So there are two primary addresses assigned to an Ethernet LAN. You find that there is physical address, then there is logical address. So logical address, this is the IP address, and the physical address, that is the MAC address. As an example, PCA can send IP packets to the file server on the same network. The layer 2 Ethernet frame contains destination MAC address. So you can see that this PCA send IP packet to the file server here. The layer 2 frame, the frame that is coming from PCA, contains destination MAC address, that is the MAC address of this server, then the source MAC address of this computer. When it comes to layer 3 IP packet, the source IP address of this computer, then the destination IP of this server. And the IP address should be within the same subnet or the same network for communication to happen. If it happens to be on the destination or remote network, that is where we factor in the essence of default gateway. So default gateway, in this case, for it to reach to the final destination, it will forward the packet to the nearest hop or next hop, which might be the interface here on this router or to the next router, so that the router can decide where to. So that's a packet tracer for identifying MAC and IP address. So when a device sends an Ethernet frame, what happens? It contains these two addresses, the destination MAC and the source MAC address, so that the source identifies the host, and then the destination identifies the recipient. To determine the destination MAC address, the device uses the address resolution protocol, which provides two basic functions: resolving IP addresses to MAC addresses, also maintaining the table mapping. It is also a question that is asked, so that ARP maps the IP version 4 addresses to physical addresses and also maintains the CAM table. So those are the functions. That's a video demonstrating how ARP broadcast a broadcast frame is sent when a device needs a MAC address. So when a device needs a MAC address or needs a general MAC address, it broadcasts that frame to the entire network, so that the associated IP version 4 address, once gotten, then it will populate the table. So on the reply, only the device with a match will reply, and the ARP reply message includes the sender IP version 4 and the sender MAC address. So when it comes to removing entries, every device has ARP cache timer that removes the ARP entries that have not been used for a specified period. That the timer differs depending on the device operating system, as shown in the figure here, so that Windows operating system store ARP cache within 2 minutes and they are removed. This is how to verify the ARP cache on Windows, and this on the router you'll use the show IP ARP to verify it. So thank you so much. If you feel have learned something on this particular day 5, the Ethernet concepts, feel free to subscribe to Netlabs Hub for more videos as of this. Thank you.